Welcome to G Fun Facts Online. Today, we are going to dismantle a 40-year-old cornerstone of planetary science. For decades, a specific image of the outer solar system has been etched into our collective consciousness. We are taught that beyond the asteroid belt lie the gas giants Jupiter and Saturn, and beyond them, in the frozen twilight, orbit the ice giants Uranus and Neptune. This classification has been the bedrock of our understanding since the Voyager 2 flybys of the late 1980s. The Standard Model paints these worlds as vast, slushy reservoirs of water, ammonia, and methane ices, wrapped in thin hydrogen envelopes. But in the quiet corridors of astrophysics departments and high-performance computing centers, a revolution is brewing. A new wave of research suggests that our fundamental classification of these planets is wrong. They may not be ice giants at all. We are here to discuss the rock giant hypothesis. This radical new framework proposes that Uranus and Neptune are not dominated by water, but by rock. We are talking about vast, hot silicate interiors that have been masquerading as ice for decades. This shift threatens to upend our understanding of how the solar system formed, how magnetic fields are generated, and how we interpret the thousands of exoplanets currently being discovered around distant stars. To understand why this hypothesis is so disruptive, we must first look at how the ice giant label came to be. When Voyager 2 swept past Uranus in 1986 and Neptune in 1989, it returned gravitational data that allowed scientists to calculate the planet's densities. Uranus at 1.27 grams per cc and Neptune at 1.64 grams per cc were denser than Saturn, yet far less dense than Earth. Planetary scientists of the 20th century worked with a limited palette of materials to explain this. They had gas, which is low-density hydrogen and helium. They had ice, meaning water, methane, and ammonia, which creates a medium density. And they had rock and iron, which are high density. To match the observed mass and radius of Uranus and Neptune, the simplest mathematical solution was a mixture that was roughly 60 to 70% ice by mass, with a smaller rocky core and a hydrogen envelope. It was a solution born of chemical probability. Oxygen is the third most common element in the universe, so water should be abundant in the outer solar system. Thus, the ice giant was born. However, the crack in this foundation lies in a phenomenon known as density degeneracy. At the immense pressures found deep inside a planet, which can be millions of times the atmospheric pressure of Earth, matter behaves in counterintuitive ways. In the Standard Model, we assume a distinct layering of a rocky core, an icy mantle, and a gaseous atmosphere. But recent work by researchers like Luca Morf and Ravit Held at the University of Zurich has highlighted a critical flaw in this assumption. At pressures exceeding 100 gigapascals, the density of a mixture of rock and hydrogen gas can be virtually identical to the density of high-pressure ice. Imagine two planetary interiors. Model A is a thick layer of water ice compressed to a super-dense state. Model B is a skeleton of silicate rock permeated by hydrogen and helium gas. To a passing spacecraft measuring gravity, these two interiors look exactly the same. Voyager 2 did not see ice. It saw a mass distribution that could be ice. For decades, we chose the ice model because we assumed ices were more common. The rock giant hypothesis asks, what if we chose wrong? The shift toward the rock giant model is driven by observational paradoxes that the ice giant model has failed to solve. One of the most compelling arguments comes from the atmosphere. If Uranus and Neptune were truly formed primarily from water ice, their formation would have involved the accretion of cometary materials rich in oxygen. As these ices churned and mixed over billions of years, chemical equilibrium dictates that some of that oxygen should react with carbon to form carbon monoxide. However, Professor Nicholas Teenby and his colleagues have pointed out a glaring inconsistency. The atmospheres of Uranus and Neptune are remarkably depleted in carbon monoxide. If the interior were a vast ocean of supercritical water mixed with the atmosphere, we should see roughly 100 times more carbon monoxide than we do. The ice giant model tries to explain this away by arguing that the planets are unmixed, meaning the water is trapped in a lower layer that never interacts with the atmosphere. But this creates thermodynamic problems. A planet that does not mix its interior struggles to cool down, yet Neptune emits significant internal heat. The rock giant hypothesis offers a cleaner solution. If the planet is dominated by dry rock rather than water ice, the oxygen budget is locked up in silicate minerals deep in the solid or molten rock, making it unavailable to form carbon monoxide in the upper atmosphere. The missing oxygen is not actually missing, it is just bound in rock, exactly as it is on Earth. Perhaps the greatest mystery of Uranus and Neptune is their magnetic fields. Unlike Earth, Jupiter, and Saturn, whose magnetic fields are aligned roughly with their rotation axes and centered in the core, the fields of Uranus and Neptune are chaotic. They are offset from the planet's center by thousands of kilometers and tilted wildly, up to 60 degrees in the case of Uranus. The standard ice giant model explains this by proposing a shallow dynamo, essentially a conducting fluid layer of ionic water moving sluggishly near the surface. But simulations have always struggled to make this work perfectly. Pure water is hard to make electrically conductive enough to generate the observed fields without extreme temperatures that would melt the planet. Recent studies into the electrical conductivity of silicates at extreme pressures have provided a lifeline for the rock giant view. We used to think of rock as an electrical insulator. However, new molecular dynamics simulations show that at the pressures inside Uranus and Neptune, silicate magma becomes a semiconductor and eventually a liquid metal. A rock giant model posits that the magnetic field is generated not by slushy water, but by conductive silicate fluids or a soup of magnesium oxide and hydrogen. This ionic rock dynamo could naturally produce the complex multipolar off-center magnetic fields that Voyager 2 observed. It turns out that a messy magnetic field may be the signature of a liquid rock interior, not an icy one. The most significant hurdle for the rock giant hypothesis is the question of origin. How do you build a planet made of rock in a region of the solar system defined by ice? The standard story of solar system formation says that beyond the frost line, roughly where Jupiter sits, ices condense into solids. Therefore, any planet forming there should be mostly ice. However, new formation models suggest we may have overestimated the purity of the outer solar nebula. We must consider refractory accumulation. As the protoplanetary disk evolved, drag forces could have concentrated dust grains, specifically silicates and carbon-rich tars, more efficiently than ice. Furthermore, we now know that objects in the Kuiper belt, like Pluto, are not pure water ice. They are covered in dark, reddish organic materials and rock. If Uranus and Neptune formed by accreting billions of these dirty planetesimals, they would naturally acquire a massive budget of rock and organic carbon rather than just water. A modern theory known as pebble accretion supports this view. In this scenario, planets grow rapidly by sweeping up millimeter-sized pebbles of dust and ice. Detailed hydrodynamical simulations show that if the gas disk survives long enough, a growing core can capture massive amounts of silicate dust that drifts inward from the outer edges of the solar system. This mechanism allows a planet to build a massive rocky core, perhaps 70 to 80% of its total mass, even in the outer solar system, provided it accretes the material before the gas disk dissipates. The result is a world that is not a ball of ice, but a massive super-Earth that managed to hold on to a thick blanket of hydrogen and helium. While the rock giant versus ice giant battle heats up, a third combatant has entered the ring, which is the methane giant hypothesis. Recent work by researchers in Israel and the United States suggests that the interiors might not be rock or water, but methane. Methane is less dense than water, but denser than hydrogen. A planet dominated by methane could solve the missing carbon monoxide problem, since methane contains no oxygen, and it fits the density data. Furthermore, at high pressures, methane decomposes into diamonds and hydrogen. This leads to the famous diamond rain hypothesis, where solid diamonds precipitate toward the core, releasing gravitational energy. While the rock giant hypothesis focuses on silicates, the methane model suggests these worlds are massive organic factories. It is possible the truth is a hybrid, essentially a rock giant coated in a thick layer of polymerized methane and diamond, with very little water to be found. The identity crisis of Uranus and Neptune matters far beyond our own solar system. The most common type of planet known in the galaxy is the sub-Neptune or mini-Neptune, planets larger than Earth but smaller than Neptune. If Uranus and Neptune are truly rock giants, it implies that rocky superworlds are the norm in the universe, not the exception. It suggests that the transition from a terrestrial planet like Earth to a gas giant like Jupiter is not a cliff, but a smooth gradient. In this view, Earth is 100% rock and metal. A super-Earth might be 90% rock and 10% gas. Uranus, under the rock giant model, would be 70% rock and 30% gas, and Jupiter would be mostly gas with a tiny rocky core. This continuum would mean that many of the mini-Neptunes we see in habitable zones around other stars might actually be super-Earths with bloated atmospheres. They could have solid surfaces deep beneath their clouds, rather than being bottomless oceans of magma or ice. This significantly increases the real estate available for potential subsurface habitability in the galaxy. The rock giant hypothesis has exposed a humiliating truth. We do not know what half of the planets in our own solar system are made of. We are modeling complex exoplanetary systems based on a template, the ice giant that might be a fiction. The only way to resolve the debate between rock, ice, and methane is to return. A dedicated Uranus orbiter and probe is listed as a top priority in the latest Planetary Science Decadal Survey. To distinguish between the models, a future mission would need deep gravity measurements. By orbiting close to the planet, a spacecraft can map the mass distribution, because a rock-dominated interior has a different gravitational fingerprint than an ice-dominated one. It would also need seismology. Ideally, measuring the vibrations of the planet could reveal the stiffness of the core, as rock rings differently than ice. Finally, we need to measure noble gas abundances. A probe dropped into the atmosphere, measuring argon, krypton, and xenon, can tell us if the planet formed from ices, which trap these gases, or rocks, which do not. The rock giant hypothesis is more than just a new model. It is a reminder of the fragility of scientific knowledge. For decades, we looked at the pale blue dots of Uranus and Neptune and saw what we expected to see: frozen copies of the comets that wander our skies. But the universe is rarely so compliant. The new data suggests these worlds are dark, hot silicate monsters, wrapped in crushing layers of hydrogen, generating magnetic fields through the churning of liquid rock rather than salty water. They are not merely ice giants relegated to the freezer of the solar system. They are the missing link between the Earth and the stars, the archetype of the most common planetary family in the galaxy. Until we return to verify the truth, Uranus and Neptune remain the ultimate Rorschach test of planetary science, mirrors reflecting our changing understanding of how worlds are built. The ice giant is dead. Long live the rock giant. Thank you for listening to G Fun Facts Online.